Welcome to our presentation on radar-based tracking simulation. In our work package, we tried to simulate all the relevant effects of a radar processing toolchain, phenomenological effects such as the environment perception, the fast Fourier transformation taking place in the high-frequency front end, as well as the data processing. To do so, we developed a modular toolchain comprising two different environment simulations. We enriched those environment simulations with OSI interfaces in order to interconnect two different radar sensor models, an object-based sensor model from FZD, as well as a reflection-based radar model from FZI. And in order to create a consistent virtual world in the reflection-based radar model of FCI, we enriched the OSI interface by open material. In the first proof of concept here, we added material and 3D model references to the open simulation interface message ground truth in order to be able to create the same virtual world in the reflection-based calculation model of FZI, consistent with the one in IPG CarMaker, in order to be able to have input from the two different environment simulations and use them in our radar system simulation from FZD, and finally use the output of this component in our system under test, which is a radar-based tracking simulation and a metric-based evaluation of object positions. But for now, my colleague takes over in order to give you a brief insight in the reflection calculation model.
I can present you a bit more about the reflection calculation. As is already mentioned, we have here one radar sensor model, and you will hear more about it later on. And we have here two OSI interfaces that forward the reflection information that is generated from the environment simulation. On the top, we have the reflection calculation directly used from IPG CarMaker, meaning the sensor is sending out rays into the environment. Indirections are followed with each ray, and if a ray comes back to the sensor, it is called a reflection, and information such as the electric field and the azimuth and elevation angles are reported. The simulation takes into account such things like the time of flight, the damping about that, the different materials on each reflection point, and something like environment effects like fog or rain. Alternatively, we have this external model. So this one is integrated in the environment simulator from IPG. This one is an external standalone reflection model, and this takes as input an OSI message, especially the ground truth information, and then uses the model references to assemble a virtual environment, and then puts also rays into the scenario and samples the environment. Maybe one different here, the direct reflection, so the last segment is emulated with a geometric physical optics formula. But at the end, it also delivers an OSI message with radar reflections containing the azimuth, the elevation, the time of flight, and the electric field strength. So for the radar model, it doesn't matter if the information is provided by IPG or by the external reflection calculation models. And for information about the radar model in detail, I give over to my colleague.
Yeah, thank you, Sebastian. I will be talking about this part, or these two parts of our toolchain. So, as explained before, we take either the output from IPG CarMaker or this stream here, so the reflection calculation. We take these reflections and we calculate the FFT output of the radar. So if you take a look at the entire radar processing, signal processing chain here, we're at this point down at the simulation where we take the reflections and smear them with a windowing function as a normal FFT would do. And then we therefore simulate the FFTs, proceed with thresholding, standard CFAR algorithms as you're used to in a radar application, interpolation, and there we get our detections. So we simulate the FFTs, the thresholding and interpolation down here in this radar system simulation. And this is the first output of the radar model. It's the detections you get, so single point detection of the radar. And then we also simulate a radar tracking algorithm, so object detection and tracking. And this is our system under test here in this use case. So the use case is we have a new tracking algorithm and we want to evaluate it against ground truth. And that's the major benefit in simulation. We do have actual ground truth where the objects are. And in this example here, we have a simple metric comparing the positions of a simulated tracking output and the actual ground truth from the simulation. And with this, we can evaluate how good the tracking algorithm and the object detection is. And this is the main use case here. And we can see this over time for different objects in the scene, how they're recognized and how far the distance is between those. And this is then the evaluation here of the tracking and the simulation use case. So in conclusion, to sum it up, we developed a modular toolchain using different inputs, different tools, so they're interchangeable. We have IPG CarMaker, we have an open source solution, so this can be used free by anyone. We have a dedicated reflection calculation, which is all connected with open materials, so we have the same material properties and the same environment simulation for these different threads we have here, and this all comes together in a radar simulation leading to tracking as an example use case. Of course, there you can think of other use cases here to use this simulation. And overall with this, we have proven exchangeability for the models. It's scalable, so it can be used on different platforms. We can run several models in parallel. We have a separation of responsibilities. All these blocks were developed by different partners, and which is only possible with a standardized interface, which is OSI in this case. And with open material, we ensure consistent environment simulation for this whole processing chain. Thank you very much.